Okay, now that we've looked at the basics of how a standing wave gets set up, in terms of what is required, in terms of the two waves that compose it, and what happens when a wave gets to a boundary, now we can look at how standing waves can get created in different situations. The first one we're going to look at is standing waves that get created on a string. So we're going, for our string, for our purposes, we're going to imagine a string that is between two kind of fixed points, okay? So the string is going to be between two what we'll call fixed boundaries, okay? There are no free ends to the string. It's tied down in two different spots. So if there are two fixed boundaries, then think about what this means for the reflections at the boundaries. That means that at each side, the reflecting waves will be inverted. Will be inverted. So, given your specific wave, or given your specific distance or length of this string, if the correct wave speed and wavelength are used, a standing wave will result. So this idea that you can create a standing wave and it will just kind of perpetuate itself because this wave keeps getting reflected back on itself and creating a standing wave, that idea has a name. That is called resonance. This phenomenon. Okay, this isn't the string itself. This is just the length that we're dealing with. So this is called resonance. A wave causes an object to oscillate in turn because of that wave. Okay, assuming no energy is lost. So here's the length that we're dealing with. Here, we're going to have a whole bunch of different standing waves that we're going to set up. So make sure to leave some space here. Let's say that this is the length that I want to, on which I have a string between these 2 points, and I want to create a standing wave. What's the simplest standing wave that could occur? If you think back to the simulation, there was a standing wave that looked something like this. There was a mode. Now again, remember what is being depicted here. This is not showing that the string is in two spots at once. These are the two different modes that the string is oscillating between. Sometimes the string will be all the way up, it'll have a maximum upward displacement, other times it'll have a downward displacement, and it's going back and forth between these two. So if you look at it, it's almost like what you see when you watch a jump rope. It looks like it goes from, this is concave down to concave up, and it just keeps doing that. Okay, so that's the simplest standing wave that could occur. And again, the reason that this occurs is because we have waves that are going in opposite directions because of this reflection, and they're getting inverted at that reflection point. Now, the key here is to try to come up with the relationship that would cause this between the length that we have on the string, the length of the string that we have to work with, and the size of the wavelength that is being used here. So if I were to ask you, okay, well, how big is this wavelength in relation to L? It might be a little confusing at first, but remember what a full wavelength looks like. This is not a full wavelength. This is only half of a wavelength. A full wavelength would be like the string going up like this, coming back to the node, and then down, and then back up, right? That would be a full wavelength. This is only half of a wavelength. So what I'm going to do is I'm going to write that L, the length of the string, in this first case, is equal to lambda, the wavelength, divided by 2. Okay, because the wavelength is twice as long as this L. You would need twice as long of a distance to make this shape for one wavelength. So if the wavelength is twice as long as L, it stands to reason that L is half of a wavelength. Okay? I'm going to leave that for a second. We're going to write a lot more, so we're going to come back to that. We could set up a different standing wave on this string for this particular length. It would look, now remember, we have to, the boundary conditions here are that these parts of the string have to be fixed right here. We have to have nodes here and here where the string does not move. It's tied to the whatever, it's tied to something on here. Okay, it's at the very ends. We can do other standing waves. We can create other modes of standing waves. It just has to be so that there are nodes at the very ends. What's another possible standing wave shape? Well, what about this? What if it looked like this? That's a possible standing wave shape, and that's one we saw in the simulation. The string would change from being on the dotted line to being on the solid line and back and forth. So again, you would have a standing wave. The string is oscillating between these two states. Now, this time, clearly, the length is not equal to half of a wavelength. Okay, this length here of the string is not equal to half a wavelength. How much of a wavelength is contained within this boundary? That looks like one full wavelength to me. So I'm just going to write L equals lambda. I could keep going. What's another type of standing wave, or what's another mode for standing waves that could exist? What about this? What if you had, let's see, do there and there. What if you had something like this? Again, nodes at the ends. What if you had something like that? It's still a standing wave. It's oscillating from the dotted line to the solid line. How much of a wavelength is contained in this distance L here? Well, in this case, we have one full wavelength and then half of another. So I could write 1.5 wavelengths, but there's actually a pattern that I want to see, and we're going to come back to these other ones in just a second. How could I write 1.5 as an improper fraction? It would be 3 lambda over 2. So I actually want to revisit the first two at this point, because maybe a pattern starts to emerge. This first one is lambda over 2, okay? And we know that anytime there's no coefficient, I could just write a 1 in here. So this is 1/2 lambda, or 1 lambda over 2. This one, there was no denominator of 2, but what if I did make it be so there's a denominator of 2? What if I wrote it like this? I wrote it as something over 2, or something lambda over 2. What would I have to put here in order to make it equal to lambda? I would have to put a 2. So you can see how this pattern might be emerging. I have 1 lambda over 2, 2 lambda over 2, 3 lambda over 2. Perhaps the next type of standing wave that would result might look something like this and follow the pattern. If I have to have nodes here and here, another type of standing wave might look like this. Again, oscillating between the dotted line and the solid line. I have 2 full wavelengths in here, so L is equal to 2 lambda. Almost wrote 2 pi for some reason. But what if I wanted to write that as something lambda over 2? What would I put? I would put 4. So I see a pattern emerging. Every time I go up one, I guess these are called modes of oscillation, I have a different number here, and the number just goes up by 1 each time. 1 lambda over 2, 2 lambda over 2, 3 lambda over 2, and 4 lambda over 2. And again, I want to stress right now, this is strictly setup work. This is not what the question would be on. This is just our way of getting to the equation that will tell us, hey, what sort of frequency is playing on these strings? What sort of frequency for the wave has to work, or would work here under these conditions. So we see that we have some sort of pattern, but that doesn't, okay, it's a random pattern. Why are we talking about this? Well, what do these numbers correspond to? Here there's a 1, here there's a 2, here there's a 3, here there's a 4. Is there anything in these pictures that corresponds to these numbers? Well, it turns out, look at the number of antinodes. This has one antinode. Remember, an antinode is where the string can have its maximum displacement. The string is oscillating between the solid line and the dotted line here. Its maximum displacement is at this location, okay? This is the antinode right here. Okay, another way of thinking about it, kind of a Regents way of thinking about it, is the number of loops in this pattern. But the antinode is right here. This has one antinode where there's maximum constructive and destructive interference. This has two antinodes. L equals 2 lambda over 2. This has 3. This has 4. So if we come up with a variable for the number of antinodes, we're going to call it n. If n is equal to the number of antinodes, then what we have as a general expression for L, depending on what type of standing wave you want to put up, is standing waves occur when the length is equal to some integer times the wavelength divided by 2. Okay? Matter of fact, we can turn this around and say that the wavelength, actually, this makes a little bit more sense actually. In order to create a standing wave, the wavelength has to be equal to 2L divided by n. And you'll notice that n is a whole number. If we didn't have a whole number here, 1, 2, 3, 4, and so on and so forth, then what would end up is you would be trying to fit waves that don't, or you would try to be putting waves that don't fit evenly into this space. You would end up with waves that just dissipate. They're not standing waves. The reason that there's only certain wavelengths that work here is because of these boundary conditions. We need there to be antinodes here and here. If you tried to say, like, plug in like 0.7, it would end up being something that would not have it. The math would work out so that there is not a node here, and that's not physically possible. So what we found out so far is that the wavelengths that will fit on a stretch of string of length L have to be equal. There's a whole bunch of them that will fit and cause a standing wave, but they have to be equal to 2 times the length divided by n, where n is known as the mode, the mode of oscillation, the standing wave mode. This is called the n equals 1, this is n equals 2, this is n equals 3, this is n equals 4. So actually I'm going to start writing that down. This is the n equals 1 standing wave. We're going to write more here, so leave some space. This is the n equals 2 standing wave. This is the n equals 3 standing wave. And this is the n equals 4 standing wave. We're going to write some more in here, so leave some space. Now, we're going to make a little bit of a jump. If we know that this equation is true, v equals the frequency times the wavelength, then we can rearrange this into f equals v over lambda, right? All we did was we divided both sides by lambda. Now we just found what lambda, the wavelength, can be in order for a standing wave to be set up here. So what we now have, if we subbed in our lambda expression over here, we have f equals v over 2L over n, where v is on top and 2L over n is in the denominator. Now, I don't like complex fractions, so what I'm going to do is I'm going to multiply by the reciprocal of the denominator. The reciprocal of 2L over n is n over 2L. So if I take v and multiply by n over 2L, I get this. The frequencies are equal to n times v over 2L. These are the frequencies that correspond to the wavelengths that are set up on our stretch of string that will cause standing waves to form. Okay? And that's a really cool derivation. That's a really simple equation as well. All right? Now, a couple things. Let's see here. So this wave speed, so we have f, the frequency of a standing wave that gets set up is equal to the n number, the mode of oscillation, multiplied by the wave speed divided by 2L, the length of the string, times 2. Let's talk about wave speed for a second. The wave speed is based on a couple things. We said before that wave speed is based solely on the medium or material that the wave is traveling through, and that's true for this string. The factors that affect the string and how fast the wave moves on the string, the wave speed is based on the tension in the string and on something called the linear density. The linear density is just, you know what a density is. Density is mass divided by volume. Linear density is mass divided by, instead of volume, divided by the unit distance. Mass divided by unit distance. So in other words, a linear density would be something like maybe 1 gram per meter could be a linear density. It's basically how thick the string is. The wave speed is not dependent, as we've talked about before, on the frequency or the wavelength. Okay? Changing the frequency does not necessarily, or will not change the speed of this wave. And just so we are clear, a higher tension equals a higher wave speed. And a thicker string will also equal, oh wait, I don't want to talk about that yet. I believe a thicker string equals a slower wave. Don't quote me on that, I haven't thought about that one yet. Okay, so what we're getting with this equation right here each frequency that satisfies the above equation creates a standing wave. Now what do I mean by that? Well, remember, the wave speed can be anything, the length can be anything, but n has to be an integer number. It has to be 1, 2, 3, 4, 5, 6, 7, going on and on forever. Okay? So, because we have a limit on what n can be, it has to be 1, 2, 3, 4, 5, 6, we have only certain frequencies that will cause a standing wave. These are the frequencies that cause standing waves. And we do have to note that this equation works for n equals 1, 2, 3, ... Okay, it has to be numbers like that. Also notice that as we increase n, basically we're just increasing it by a multiple of v over 2l. So f goes up a set amount between each pair of modes. The frequency will go up by a set amount each time. Okay, now the last thing I want to write down is there are other names for these types of oscillations. We don't just refer to them as n equals 1, n equals 2, n equals 3, n equals 4. The n equals 1 is known as, and this is very important, the fundamental frequency. Okay? That is known as the fundamental frequency. It's also known as the first harmonic. N equals 2 is the second harmonic, and it's also known as the first overtone. Okay, so fundamental frequency is n equals 1. It's also the first harmonic. Then the harmonics are basically just the names of, whatever the n value is. N equals 2 is second harmonic. N equals 3 is the third harmonic. And the second overtone. I guess overtone means how many tones over the fundamental frequency you are. N equals 4 is the fourth harmonic. The third overtone. Okay, so this equation right here, f equals n times v over 2l for n equals 1, 2, or 3, what it does is it tells each harmonic's frequency. And that's why this equation is so important. If you have waves that you're trying to oscillate on a string, there are many, many ways that those waves can be set up. And that equation, F equals n times V over 2L, tells us what the frequencies are that will create standing waves. If standing waves are being created, here are the frequencies of the waves that will cause this oscillation. That's kind of a lot. Make sure, if you need to, make sure to watch this again. Feel free to ask questions on this. We'll take a look at this more in class. We'll do lots of examples. When you come back for the next video, we're going to be talking not about waves on a string, but instead sound waves in a tube, which is very similar.